Hi everyone. In this video I will go through an example and show you how to draw the root locus for a given system. So here we have the process or the plant given as the transfer function that you can see here, where we have a pole at 1 and we have two complex poles. Let's see where are the complex poles located for this system. So s squared plus 4s plus 7 equal to 0 will give us S1 and 2 located at minus 4 plus minus square root of 16 minus 28 over 2, which will be equal to minus 2 plus minus j square root of 3. So we have poles of the system located here at 1 and minus 2 plus minus j square root of 3. So we see that for this system we have n equal to 3, we have 3 poles. We have m equal to 0, there is no 0 for the system, and as a result r, which is equal to n minus m, is equal to 3 minus 0, and it's equal to 3. Therefore we know that we have 3 asymptotes for the root locus of the system. Since we have 3 asymptotes, we need to find out xa, point of abscissa, and kca, the angle of the asymptotes with the real axis, in order to be able to draw the asymptotes. So how can we do that? We know that xa is equal to sum of zi's minus sum of pi's over n minus m. So keep in mind that zi's and pi's that we use here should be obtained from the system represented by the events form. And by the events form we will have gp1 of s equal to s minus 1 over s plus 2 plus j square root of 3, s plus 2 minus j square root of 3, and from here we have p1 equal to minus 1, because it's indeed in this format, s plus p1, s plus p2, s plus p3. So we have p1 equal to minus 1, p2 equal to 2 plus j square root of 3, and p3 equal to 2 minus j square root of 3. Therefore xa is equal to, there's no zi, there's no 0 for the system, so we have 0 minus sum of pi's, minus 1 plus 2 j square root of 3 plus 2 minus j square root of 3 over 3, and this will give us minus 1. Therefore xa is equal to minus 1, the abscissa point. To find out kca, we have r times kca equal to 2h plus 1 times pi for the positive locus and 2h pi for the negative locus. And r is equal to n minus m, which is 3. We can, since here we have 3 asymptotes, we will use h equal to 0, 1 and 2, and therefore we have, replacing h with those values, we will have pi, 3 pi and 5 pi for the positive locus, 0, 2 pi and 4 pi for the negative locus. And r is equal to 3, as a result kca will be equal to pi over 3, pi, 5 pi over 3 for the positive locus, and 0, 2 pi over 3, 4 pi over 3 for the negative locus. So we know the abscissa point, we know the angles of the asymptotes, therefore we can start to draw the asymptotes. Let's prepare a graph for the positive locus. And another graph for the negative locus. So this is for negative locus, and this one is for the positive locus. Let's determine the location of the poles of the system. We have one at 1, and we have one pole at -2 plus j square root of 3, and one at -2 minus j square root of 3, and the same thing here. So now we can start to draw the asymptotes. Point of abscissa is 0, -1. For the positive locus, we have asymptotes with angles of pi over 3, pi, and 5 pi over 3. So if I draw the asymptotes, we will have these asymptotes, as you can see here. These are the asymptotes that we have for the positive locus. For the negative locus, we have 3 asymptotes with angles of 0, 2 pi over 3, and 4 pi over 3, originating from the point at -1. So this is one asymptote on the real axis. Here we have the second asymptote, and we have the third asymptote like this. So for this special example, we see that the asymptotes indeed cross the poles of the open loop system. So it might not be always the case, but for this example it is. Now we can determine as the next step which parts of the real axis belongs to the root locus. So here we have 2 segments in terms of the number of poles and zeros on the right hand side, whether it's an odd number or it's an even number. From -infinity until, or let's say we have 3 segments, until -2, we have 3 poles on the right hand side. From -2 until 1, we have 1 pole on the right hand side, and from 1 till infinity we have 0 pole on the right hand side. As a result, we can see that these 2 segments belong to the positive locus, and this segment belongs to the negative locus. So we can determine it on the graphs. From -infinity till +1 belongs to the positive locus, and from 1 till infinity belongs to the negative locus, as we can see here. So then as the next step, we can think about the break-in or breakaway points. Break-in or breakaway point. We have n of s equal to 1, and therefore n prime of s is equal to 0. D of s is equal to s minus 1 times s squared plus 4s plus 7, and as a result, d prime of s could be written in the form of s squared plus 4s plus 7 plus s minus 1 times 2s plus 4. So we will have n prime d minus d prime n equal to 0. N prime is already 0, so we will have only minus d prime times n, and since n is equal to 1, we will have only d prime. minus d prime equal to 0, or indeed d prime equal to 0. D prime equal to 0 will provide us s squared plus 4s plus 7 plus 2 times s minus 1 times s plus 2. And from here we will have s squared plus 4s plus 7 plus 2 times s squared minus s minus 2. S squared plus s, sorry, plus s minus 2. So we will have 3s squared plus 6s plus 3 equal to 0, or s squared plus 2s plus 1 equal to 0, which will provide us s plus 1 squared equal to 0. As a result, we will have two roots at minus 1. And by looking at the on the root locus plots that we have here, we have already started, we see that the point minus 1 belongs to the positive locus, and it is here. So this will be our break-in or breakaway point, and indeed, in this example, it is both a break-in and breakaway point. Why? Because we will have branches coming from the poles, arriving at this point on the real axis, and afterwards they will depart and they will move on the towards the infinity using the asymptotes that we have here. And we don't have any break-in or breakaway point for the negative locus. So as the next step for this example, we can find out the departure angle from the poles. Departure angles. We have q times alpha departure, where q is the number of multiplicity of the poles, and here we have only one, equal to sum of phi i's minus sum of theta i's plus 2h plus 1 times pi for the positive locus, and sum of phi I minus sum of theta I plus 2h pi for the negative locus. So let's say that we want to find out the angle of departure for the pole at minus 2 plus j square root of 3. To find out that angle, we need to take into account the other poles and zeros. Since there is no zero in this system, the phi i's will disappear. We have two more poles if you want to find out the angle of departure for this pole. To find out theta 1 and theta 2, what we need to do is to connect each pole to this point, as we have it here, and then draw a line from that pole towards the plus infinity. And here we will have the angle theta 1. And for the second pole, we will have this angle as theta 2. So it's obviously theta 2 is equal to pi over 2. And here we have this angle equal to pi over 6, or 30 degrees. As a result, theta 1 will be equal to 5 pi over 6. So theta 1 is equal to 5 pi over 6, or indeed 150 degrees. And here we have 90 degrees. So therefore we can find out the departure angle, and q here is equal to 1 because we have only one pole at that point. So we will have departure angle equal to sum of phi i's 0 minus sum of theta i's 90 degrees plus 150 degrees plus 2h plus 1 pi, and since here we have only q equal to 1, so h will be equal to 0 plus pi for the positive locus, and 0 minus 90 degrees plus 150 degrees plus 0 for the negative locus. So the departure angle will be equal to pi is 180 minus 180 minus 90 plus 150 will be equal to 240, and it's equal to minus 60 degrees or minus pi over 3 for the positive locus, and minus 240 degrees for the negative locus. Minus 240 or minus 4 pi over 3. Okay, so we can now draw this part on our root locus. For this pole, we have the angle of departure equal to, for the positive locus, we have it equal to minus pi over 3, as we have obtained, and indeed it is like this. So the branch will start from that pole, it will depart the pole with that angle, and eventually it will arrive on the real axis at the point minus 1, the break-in point indeed. And for the other pole, we have, since the root locus is symmetric with respect to the real axis, we will have this situation. So there is no need to calculate the angle of departure for this pole. What do we have for the third pole here? It will start from the point at 1, and it will stay on the real axis. It will move towards the minus infinity on the real axis. After this point, one of the branches will continue towards plus minus infinity. One will continue on the first asymptote here, and the third one will continue on the third asymptote that we can see here. So it isn't it like this. Oops. So what do we have for the negative locus? So this pole at here, it will move towards plus infinity on the real axis. The angle of departure for this pole, indeed, for the negative locus is equal to minus 4 pi over 3. And if we draw the branch starting from this, we will obtain this branch. And due to the symmetry, we will have this as well. So indeed, in this way, we have the final result for the root locus for both negative locus and positive locus. For the positive locus, k is bigger than 0. For negative locus, k is smaller than 0. We need to determine for which value of k our system is stable. Looking at the negative locus, we can see that for any value of k smaller than 0, the closed-loop system is unstable, because we will have one pole here in this area. For the positive values of k, we need to find out the value of k at this point, where we have j square root of 3. For the corresponding value of k, we will be in a situation that it is called the marginal stability. Let's see how to find the value of k over there. So at that point, we need to determine k, which is equal to rho for this example. we need to refer to the amplitude condition. Amplitude of n over d evaluated at some s star is equal to amplitude of 1 over rho, or it's equal to amplitude of 1 over k for this example. We don't have any zero, so amplitude of n is equal to 1 over amplitude of d evaluated at that point could be obtained in this way. So we can just find out the distance of the poles with that point. So obviously this is equal to 2. This distance here can be calculated because here we have 2 and here we have 2 square root of 3. As a result, here will be equal to square root of 4 plus 4 times 3, which is 12, or square root of 16, which is equal to 4. So we have 2 for the distance of this pole from that point, 4 for the distance of the second pole from that point, and the only missing one is this distance. Distance of the third pole, and that's somehow easy to find out, because here we have 1, we have square root of 3, so as a result this will be equal to square root of 1 plus 3 or 2. Therefore here we have 2 times 4, which is equal to 1 over 16, equal to 1 over amplitude of k, and since k is positive here, we can say that k is equal to 16. Therefore, we can say that in general, if k is bigger than 16, our system will become unstable. For values of k smaller than 16 and bigger than 0, the closed loop system is stable. And then we are done with the analysis of this example. We just need to find out, to plot the root locus using MATLAB and verify our results. So that's something that I can do it right now. So I already have declared the system here, our transfer function that we had with the poles at -1 and -2 plus minus j square root of 3. To draw the root locus for the system, I can use r locus of g. And here we have the positive locus. And as you can see, it's exactly the same as what we had in our analytical solution. Yeah? And for this point, we have the gain equal to 16. So it's exactly 16 on the j omega, and again it confirms what we have obtained. We can also draw the negative locus by r locus of minus g, and again you can see that it's exactly the same as what we had in the analytical solution or sketch of the root locus. Okay, so that's all for this video. I hope you have enjoyed it and have learned something on sketching the root locus diagram for the given system. Thank you for watching, and see you next.